Hi, Physics 1. Thanks for watching. We did an experiment today in class, but I wanted to make sure that we did everything correctly. Let's talk about the buoyant force and when we submerge something in water. Because if we put water on the scale and then we put something inside of it, the weight on the scale is going to change. So in my picture here, I've got this digital scale, which is pretty accurate. I can get down to within a gram basically, and I've got my container here. So I'm gonna put this way, and the weight of the container is not important, so we are going to hit 0 and make that 0. Now I'm gonna take my container of water over here and I'm gonna pour in, let's say, 700 milliliters of water. Now, I don't know if my table is 100% level, but we're sure gonna try. Okay, so let's see here. Get up right to that 700 line and we'll see how close we can get. We're at 708 and that's pretty close. We're gonna get right to. Okay, so I'm gonna take some water out of here. Let's see here. How can we remove some water? Well, we want to get right to 700. So I'm gonna take some water out of here. The back of my container. And there we go. That's about as close as we can get to 700. Oh, we need a few more drops in there. Almost. Okay. Well, there we go. 700. Okay, so it's about right at the line. My table is it's pretty level. So, and this is about what we would expect within the our uncertainty. So we see here that 700 milliliters weighs 700 grams. That means that the density of water is about 1 gram per milliliter, or 1 gram per cubic centimeter. Okay, so now we need to do some more measurements. Okay, so let's take this empty container here. Alright, so I've got, this is green, that's why the top looks invisible. Wow, that's my invisible container. Wow, you thought I could make an invisibility device. Okay, so I'm going to put this on here. It has a green lid, so it looks invisible, not in this camera. Okay, so I put it in there, and we see that our container here weighs 10 grams. As we added our floaty container here, that went up by 10 grams, and so now we have our little container there. It is floating and it is on the surface of the water. Okay, and the weight has gone up by 10 grams roughly. It was 10. I don't know what happened to that extra. All right, so 10 grams. Let's take some water out of there. So that is right at, okay, so this is a little bit 9 grams. Okay, I'm going to make a note of this on my, right there. So the container is 9 grams. Okay, 9 grams of water. All right, so we got that down. Okay, so our container weighs 10 grams, but we don't actually know how much water can fit inside of the container, because the walls of the container have a volume. It's not completely thin, and so if we want to be really precise, we're going to have to take into account, find out the actual volume inside of the container. Now, we don't actually know, but there is one way to find out. Okay, so what I'm going to do is I'm going to take my container here, I'm going to put it underwater. I'm going to remove all of the air. So we're going to fill up this container with water. Okay, we will take it out. So do we have any bubbles? No, we do not have any bubbles. And let's see how much we've removed here. I got some on my hands, but it looks like, and I got my hands wet. All right, we're going to put some in there. So we'll say I probably lost a milliliter. That's going to be, about 658. So let's see. So we had 7. Okay. So 7 minus 658. So 700 minus 658. That is going to give us 42 grams of water. All right. That is in my container right here, and it's my invisible container, so that's full of water. Okay, so this has 42 grams of water. If I know that the density of water is 1 gram per milliliter, or per cubic centimeter, then we can say we know what the volume of one of those containers is. It's going to be 42 milliliters. Okay, so now we know the volume of liquid in here is 42 milliliters. All right, so let's fill up our container again. Okay, so we'll switch units to keep the scale from going to sleep. There we go. We're gonna fill this back up to 700 milliliters. Okay. Now this is trying to do an experiment online, right? And we're going to consider all of the forces here acting on it, and we're going to see what the buoyant force is. Okay, so we're going to go back to 700. Why am I picking 700 grams of water? It's just a nice even number. Okay, so in here we have a mystery liquid. Okay, now this has a small weight in it. It's a titanium weight down at the bottom, and the titanium weight, it looks something like this. It's a little square. This is it's a cube. It's for a pine wood derby, and I know that this weighs pretty close to 5 grams, as close as I can get to 5 grams on this digital scale. So I have a 5 gram weight of titanium. Okay, now what is the volume of here? Because as we put in a weight inside of this liquid, we don't know what it is, and we've got 2 here. Yeah, that one's, hopefully this is the one that I think it is. Okay. Now when I look at this, I notice that it's a little bit cloudy. Okay, so if you can see in there, I don't know if you can see in there, and it seems pretty viscous. Okay, so it doesn't seem quite like water, but it's definitely clear. So we want to figure out what this liquid is using density and volume and the mass. Okay, so I put a 5 gram weight in here just so that it is almost completely submerged in here. Okay, so let's do our initial measurements. Okay, so this thing is pretty much submerged, and we see that the weight of has increased. Okay, so it is definitely floating in there. Okay, so I'm gonna write this down. The blue container has a mass of 752. That's including the water and everything. 752 grams. Okay, now going back to this other liquid over here, which we now know is water. If I put this inside of here, I'm gonna take out my this mystery liquid, which we're trying to figure out. We recorded its mass. This is just water with no weight in there, and I'm gonna put it in there. And now this is 750, but it's sticking up out of the water. Okay, so this is 750. So we'll say green container is 750. Okay, and there's a little bit sticking up there. Okay, so it is not it's a little bit floaty. Okay, and we are going to try and counterbalance this by putting some mass in here. Okay, so we're gonna put a weight in here. Now there is a bubble in there, so I'm gonna have to open this underwater, let the air out, and close it and get rid of all the bubbles. And those two mystery liquids, let me tell you, it was not easy and very clean to get the water. Oh, I made a huge mess, but that's okay. It's all for science. Okay, so now I put this in here because I wanted it to be pretty close to submerged as possible, and now it is not floating anymore. Let's see how much water we have in there. Okay, so we lost a few milliliters of water. We're gonna add those back in there because we're trying to be as precise as we can. 700. There it is. I'm gonna dry this off. Okay, this is our green one, which has water in it. Okay, and it's underwater, and it is 756. Okay, so the green container with the mass in it is at 756. Okay, now the blue container was at 752, and it also had a weight in it. We did that so that it was as close to submerged as we could get. So let's see here. Now every time we take this out, we lose a little bit of water. Oh, that's pretty good. 700. Okay, we got most of it off. Okay, we'll put this guy back in here. And this one we do have a little bit of the top sticking out. Okay, so we're losing a little bit of volume. But that is 700, and I have 753. Okay, so if I push that under, how much is our mass change? Okay, so it doesn't really. That's pretty close to neutrally buoyant. Alright, not exactly, but. Alright, it doesn't change. So we're within a gram, even if it's completely submerged. That's good. That's what we wanted. Okay, so that's under 753. Okay, so we had water and our mystery liquid, which we don't know, and now I have an empty container. Okay, let's put that underwater because we are experimental physicists and we like to do experiments. We like to try things. So let's put this underwater. Okay, now this one is empty. And if I get this totally underwater, so just my fingertips are under there. Let's see here. That is 700 and. Trying really hard. About there. So let's see. That's 752. 752. Okay, so that is an empty container. Empty container, maybe 753. It's really hard to say. So empty container is 700, and we'll say 52. And it's hard to say when it's completely submerged, so we're going to have a little bit of uncertainty in our measurement there. All right, so let's get that in there. Maybe 754. All right, so we're going to say 753 plus or minus 1 milliliter. That's about as precise as I can get. Now, when the empty container there is just floating, we see that it is 710 milliliters. Okay, so that means what's going on here is, when this thing is floating on the top here, it's displaced a little bit of water. Okay, so as this presses down, the level of water goes up. Okay, and so there's a buoyant force pushing up on our thing here. Okay, so the buoyant force pushes up on our container, and we see that there is more force. The weight has increased on our scale. Okay, so there's a greater force pushing down on this. So if we considered the entire thing, because it's resting on our scale here, okay? So if we consider the center of mass of this thing, okay, well, there's more mass on the scale now, and so it's pushing down, okay? And it doesn't matter if there is a liquid here. The liquid is being forced into this container by gravity. Gravity is pulling down on it, and so there's more mass pulling down on it. So we have increased our force, so we can think of it as the water's pushing up on it, but the container is also pushing down on the water here, right? So the water pushes down with the equal force to the buoyant force, okay? And the net result is that the mass, the weight of our container has increased. All right, so we have one more mystery liquid here, okay? It's this dark liquid. We don't know what it is, but we're going to put it in there, okay? And we're going to look, and oh, this one sinks, okay? So it just goes straight to the bottom, okay? So we can say that this one is more dense than water. If the density is higher than water, it's going to sink, okay? So what that means is that the buoyant force is less than, the buoyant force is not enough to keep it floating. So the force of gravity is pulling it down, and it's greater than the buoyant force. Okay, so for this one, our dark liquid here, we get a total mass of 768 grams. So let's review what we recorded. Originally, we had 700 grams of water on the scale. When we filled up the container completely, there were 658 grams of water left in the big container. That means the water can hold 42, the small container could hold 42 grams of water. What that means is, since the density of water is mass divided by volume, or 1 gram divided by 1 milliliter, roughly, that's going to give us a density. That means that we're going to have a volume of 42 milliliters. That's how much liquid one of those containers can hold. Okay, so the blue container has a mass of 753. All right, which one was the blue container? Oh, yes, the green one is water. At least I think it's water. No, I can't. Yeah, that seems like water. And I'm shaking it around because yeah, I'll have to go back. Yes. There's also a difference in viscosity, which is a big clue, okay? The blue one is a lot more viscous than the green one. So this is another clue as to what it is, okay? So as I shake the green one, it moves around quite a lot. But as I shake the blue one, I can feel that the titanium weight is not moving around in there as quickly as this one. So this one is a much more viscous liquid, okay? And these are common household things, so that should already be a big clue as to what it is. But we're going to confirm its density and then find out what it is using its density. Alright, so our blue container with the mystery liquid had a mass of 753. The green container, when we put the mass inside, so this one here is with mass, we'll call it WM. This one is without. So the green container had a mass of 750 when it was full of just water, okay? And this one had with the weight inside, had a mass of 756, okay? Now, when I submerged the container, it had a mass of 753, okay? So our dark liquid, it had a mass of 768 grams, and there was no mass inside of there. All right. So what did we find out was the mass of our container? That was 9 grams up here. So let's get the mass of our dark liquid. This is going to be the dark liquid plus container is 9 grams. So we'll subtract off the mass of our container. And so this is going to give us a total mass of 759 grams for the liquid. Okay. Then minus the 700 grams of water, so we'll say 759 minus 700 is going to give us 59 grams. All right, so that's the mass. Now we're going to find the density of that liquid. So the density of the liquid is 59 grams divided by 42 milliliters. Then I'll switch over to Mathematica, and I'll say 59 grams divided by 42 milliliters. That will give me, oh, I want the decimals. You have to put a decimal place there. Okay, so that's going to give me a density of 1.4 grams per milliliter. All right, 1.4. Oh, we opened a new window. No. All right. There we go. 1.4 grams per milliliter. One student guessed balsamic vinaigrette, and it turns out that the density of balsamic vinaigrette is 1.37 or 1.37 grams per milliliter. So we got about 1.4, but this could be really close. This might be within our uncertainty, because if we're realistic, how certain can we be? But let's look at some other common household liquid. Another guess that a student had was motor oil. Let's take a look at the density of motor oil. It certainly looks like motor oil. And we'll say grams per milliliter. Why not? All right. So we can see here that this, if for SAE 15W40, we get a weight of 0.87 grams per centimeter. So we'll say oil, and that is 0.87 grams per milliliter. Okay. So let's look at what we've got here. Balsamic vinaigrette is more dense than water. So we'll say water here, H2O, has a density of 1 gram per milliliter, roughly. Now this, strictly speaking, this changes with temperature, but we'll say 1 gram per milliliter is close enough. So balsamic vinaigrette is 1.37 grams per milliliter. This would mean that balsamic vinaigrette would sink, while oil here is going to float, because it is less dense than water, and things that are less dense usually float to the top. this brings us to why boats float. Okay? So if a boat is too heavy, it will sink, but we'll talk more about that in a minute. But what we can say so far is that oil has a lower density than water, 0.87 grams per milliliter. We did have a container full of oil, but we're going to have to take into account the weight that was in it, because we did have a 5-gram titanium weight. So, now for our mystery liquid that's very dark, we saw that it had a density of 1.4 grams per milliliter. So, it's a little bit more than balsamic vinaigrette. What else could it be? Well, another common material is molasses. Molasses are also very dense, and according to Google, the density of molasses is 1.42 grams per centimeter cubed, or 1.42 grams per milliliter. So, indeed, it is molasses. We were pretty close. We were within, say, 1.42 grams per milliliter, so I'd call that a win. But we still have some uncertainty because it didn't actually match it exactly, and we don't know what kind of molasses this is. But we are definitely within the uncertainty for this one. So what we can say is it is either most likely balsamic vinaigrette or molasses. Probably not motor oil, because motor oil, would it sink or would it float? Questions. But let's go to our mystery liquid. What could it be? So for the last one, let's draw a cartoon here. We had our container here of mystery liquid, okay, and we also had a 5-gram titanium block inside of our liquid, okay, and this one was floating, okay, and we have some kind of liquid inside of here, and it was almost completely submerged, okay. So, according to what we recorded, the green container... blue container has... I forgot which container was which. Yes, the blue container, this one had a mass of 753. Now, the real question in here is my titanium block. So this was the whole thing right there. Water, container, titanium block. So, how do we get the density here? Well, we have this titanium block in here. So we're going to have to add this to the rest of our container. So we will change our container, and we need to find the new volume of liquid in there. Okay, so first we need to know what is the volume of a 5-gram weight, a cube of titanium. Okay. If we Google the mass or the density of titanium, we see that it is 4.5 grams per milliliter. So 4.5 grams per milliliter cubed. Alright, so their density of titanium is equal to 4.5 grams per milliliter cubed. We have 5 grams, and we want to know what the volume is. Okay, so density is equal to mass divided by volume. We don't know what our volume is, but we know that it's titanium. So we can say that this is equal to 4.5 grams divided by 1 milliliter. We're using milliliter because that's we're working in milliliters. That's easiest with liquid. Okay, so we want to find out our volume, so we're going to say, alright, we will multiply both sides by volume here, right? So that'll give us a volume of, yes, our volume will equal our mass times 1 milliliter divided by 4.5 grams. Okay, so our mass was 5 grams. There we go. And my head is in the way. There we go. So, 4.5 grams. Then, there we go. Alright, so we'll put in 5 grams for that. We will say 5 grams times 1 milliliter divided by 4.5 grams will give us our volume. Alright, so switching over to now, we will say 5 divided by 4.5 is going to give us 1.1 milliliters. So 1.111 milliliters. That is our volume. Alright, now the titanium block doesn't really take up that much volume, but we're trying to be as precise as we can. So we're going to take into account that volume. So our total volume inside of the container of liquid that we could have was 42 milliliters. Right? We'll subtract the volume that we found over here, minus 1.111 repeating milliliters. This is going to give us 40.999 milliliters. Let's check that on Mathematica. Where's my mouse? So the answer is 4.889. I was wrong. So I'm going to change that to 4.89. There we go. All right. I don't know how I messed that up, but probably because I'm streaming. All right. So now we have the new volume of our container, and we can find what its mass was. All right. So its total mass was 753 grams. This was the water. Mass, everything. We'll subtract off the water, 700 grams, minus the container, 9 grams, minus the 5 gram titanium block. Alright, now we're going to be able to find the density of our mystery liquid. Okay. Alright, so we're going to have 753 grams, the total mass of everything, including the water, the oil, the container, and the titanium mass. We'll subtract off the mass of the water. Then we'll subtract off the mass of the container. Then we'll subtract off the titanium mass. And now we have 39 grams. Okay, so 39 grams. This will give us 39 grams. And we found our new volume here. Okay, so 39 grams divided by this number, so we will have 39 grams divided by 4.9 or 889. This is going to be our density. Alright, so we'll have 39 grams divided by 4.8889 milliliters. We'll put in our units. So this is grams. We'll have milliliters here. And that gives us a density of 0.9538. Now, this is less than the density of water, even if you consider the size change. The density of water can range anywhere from 1 gram to 0.995 grams. Okay, so if we did everything right, now we need to find a liquid with this density. And let's see if common household items might have this density. Okay, so if we Google the density of vegetable oil, then we see that it is 0.93 grams per centimeter cubed. We got an answer of 0.95 grams. So what I would say is that we are definitely within the uncertainty of our measurement, and it could very well be cooking oil. But let's look at different types of oil. So density of vegetable oil, I will write that down. So vegetable oil is 0.93 grams per milliliter. Let's try canola oil. maybe they're different. Canola oil. Oh, canola oil is a little bit different. Alright, so that is 0.92 grams per milliliter. And let's try olive oil. Why not? Olive oil, grams per milliliter. Oh, 92 grams per milliliter. Let's try motor oil. We already did motor oil, but let's try it again. Motor oil is 0.087. Okay, so what have we found? Well, it's probably vegetable oil. It's a little bit heavier, but we really can't say, at least with the measurements that we did, we are within the uncertainty. All we can say is that it is some type of cooking oil, most likely. It is clear. That makes me think it's not motor oil. So it's definitely some type of cooking oil. Probably not motor oil because we can see through it. And I use stuff out of the kitchen. Okay. So we were able to, using the density, distinguish between different types of materials. This was thanks to our good friend Archimedes, who was able to use this method to deduce what a crown was made out of. According to legend, Archimedes wanted to find out what a crown was made out of after the king had given a bunch of metal to a metalsmith to make the crown. So when the king got it back, he didn't know if the jeweler had tricked him and basically put lead in for it, and they didn't want to destroy the crown because it was obviously very hard to make, and so they wanted to find a way to figure out what material it was made out of. So they of course consulted the wise men, which Archimedes was one of them, and so he thought about this problem, and as he was taking a bath, Archimedes realized that the water level went up and he was displacing a certain amount of water. Well, if he knew what the density of pure gold was, then he could figure out the volume of the crown and determine if the same amount of gold displaced that much water and had the same weight. And so he was able to determine what the crown was actually made out of. Of course, he immediately jumped up out of the tub naked, ran through the streets screaming "Eureka!" And that's a story for another class. But a certain amount of material will displace a specific volume of liquid. Each material has a different density. Gold is heavier than lead. Lead's pretty heavy, but it's not as heavy as gold. So he could figure out, well, if I know, say I have 1 kilogram of lead, I know that it should displace this specific amount of water, which is different than gold. If you have the same mass of gold, it's going to displace a different amount of water than lead. So if you ever want to know what something is made out of, you can use Archimedes' principle to determine what that material is. Thanks for watching, and I will see you again tomorrow. Alright, let's do one more experiment. Let's talk about Archimedes' principles. Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. Archimedes' principle is a law of physics fundamental to fluid mechanics. It was formulated by Archimedes of Syracuse. Let's talk about what that means exactly, because sometimes when we read these things, it just seems like a lot of words. Alright, so Archimedes' principle states that the upward buoyant force that is exerted on the body immersed. So when we put in a material into our liquid, the liquid pushes it up. That's why things float. There's a buoyant force. The liquid is pushing back on to the container of whatever you put in there. Okay? That's because when you push a container inside of the liquid, okay, it pushes the liquid up. The level of water rises, and the water wants to fall down. So as we displace fluid, water is not compressible. The water wants to flow back, and so we're raising the water level. And so there's going to be a force that pushes on the container. We can feel it when you push down on it. The water pushes back. When I sink this container down, it's pushing back. It wants to go back up. That's the buoyant force. Okay, so now we're going to fill this container up to the tippity top. If we can do this, I might need to get some more water. And now we need to put on our. Don't forget to turn that on. Okay, we're gonna turn this. We're gonna fill this up to the very tippity top, and we're going to. Yes, we're gonna get it to the very top, and I'm probably gonna need some more water. I think we can do it. Okay. We are at. It is just brimming over there. Oh man, it is so full right now. Don't bump the table because it's gonna break the skin. Alright. So that is just brimming over. Wow, and it's only the tension of the water. Let's add a couple more drops. Let's just see. Okay. Oh wow, that's really full. Okay, so we want to see. We're gonna change that. We're gonna put that at 0. Alright, so we're going to put an empty container in here on the top of my water. We're going to adjust this up so we can see it a little bit better. There we go. But we need to see. Oh, it's not working. Alright. Put my big head. Oh, no, that's the wrong one. Oh, too many windows. Too many programs. There, I'll put my big schnoz over there. Alright, so we're going to get this, make sure it's not touching. Oh, it was touching. Oh, jeez. Okay. So now we're going to collect this water. We're going to put our empty container on here. And yes, it is. No, we're losing water. Oh. I'm going to collect this water. Oh, it's dripping. It's dripping. How much of it? Oh, no, it's going on the table. Oh. Failure. Okay, we're gonna try and collect that water. Just a second. So we collected 9 grams of water. Let's see how much our container actually weighs. Okay, this is the ultimate test here. Okay, so we've got our container here. Get all the water off here. And our container is 9 grams. Actually works. What the heck? There was a little bit of water. It kept kind of flowing over there. But it just kind of dribbled down the side. So we're going to ignore that because we did get 9 grams of water in here. Okay, so what that means is... Oh, and now it says 10. I think we got a couple drops over there. Alright, well, it was 9 grams. There's a little bit of uncertainty. Okay, so what that means is that as we put the container on here, it pushed the water into our container right here. We are going to repeat the experiment. This time we're going to try and collect water more accurately. We're going to fill it to the tippity top. Yes. There we go. Oh! Nope. We're losing some water there. Okay. We need to get this to stop. All right, there we go. We had a little accident, but we are going to carry on. Okay, so now we're going to say we're going to measure the weight of one container. All right, so we're going to put this on here. Say this is 0. Container is 10 grams. We're going to put this on here. All right. So when we put our empty container in here, actually we'll add some weights. Okay, so we will add 2 weights to our container. So let's put this at 0. Get our water off. All right. So the mass of our container with the 2 weights is 19. All right. So now we're going to attempt to collect water here. And we're going to see how much water it will displace and we can collect. Redo. We need to get this more full. That's the issue.
Thank you, like and subscribe down below.